According to the physics textbook scientists were working from in 2012, there was a wall waiting for Voyager 1 at the edge of the solar system, a wall that should have been somewhere between 50 and 70 times the distance from the Earth to the Sun, thick, a slow, gradual transition zone separating our solar system from the rest of the galaxy. Voyager 1 crossed the actual boundary in a fraction of that distance, and on the way there, it spent months drifting through something that, according to the same models, wasn't even supposed to exist at all. This is the story of what Voyager 1 actually found waiting at the edge of our solar system, a boundary that turned out to be both far thinner and far stranger than anyone had predicted, and a strange transitional region that NASA scientists ended up nicknaming the Magnetic Highway. Stick around, because the details behind this discovery genuinely forced physicists to rethink what the edge of a solar system is supposed to look like, and if you want to catch every new discovery coming out of this incredible decades-old spacecraft, go ahead and hit follow before we get into it. To understand why this particular boundary caused so much confusion, you first need to understand the basic structure scientists expected to find there. Our entire solar system sits inside an enormous bubble called the heliosphere, inflated outward by the constant stream of charged particles flowing from the sun, known as the solar wind. That bubble doesn't just stop abruptly. Physicists modeled it as a layered structure, similar in some ways to the way Earth's own atmosphere thins out gradually rather than simply ending at a hard line. The first layer, called the termination shock, marks the point where the solar wind abruptly slows down as it starts running into resistance from the material of interstellar space. Voyager 1 crossed that first boundary back in December of 2004, at a distance of about 94 times the distance from the Earth to the Sun, a unit astronomers call an astronomical unit. Beyond the termination shock lies a much larger, more turbulent region called the heliosheath, where the slowed solar wind gets compressed and churned as it continues pushing outward against the interstellar medium. Somewhere beyond that lies the heliopause itself, the true outer boundary where the sun's influence finally gives way entirely to interstellar space. Based on models of how the solar wind should behave as it collides with material from between the stars, physicists estimated that this entire transitional zone, from the termination shock to the heliopause, should stretch somewhere between 50 and 70 astronomical units. Thick, an enormous, gradually shifting buffer separating our solar system from the wider galaxy. Voyager 1 crossed that same distance in roughly 28 astronomical units, according to later analysis of the crossing. In the specific direction the spacecraft happened to be traveling, the sun's protective bubble turned out to be dramatically thinner than the models had assumed, nowhere close to the sprawling, gradual buffer zone scientists had spent years calculating. That alone was a significant surprise, but it wasn't even the strangest thing Voyager 1 found on its way through. For months before actually crossing the heliopause, throughout the second half of 2012, Voyager 1's instruments began recording something bizarre. The number of low-energy charged particles native to our own solar system started dropping sharply, the kind of decline you'd expect right before finally leaving the sun's influence behind. But at the exact same time, the direction of the magnetic field surrounding the spacecraft wasn't changing at all. It was staying locked in, essentially the same orientation. Associated with the inside of the heliosphere, even as the particle population around the spacecraft was behaving as though it had already left. Mission scientists started calling this strange in-between region the Magnetic Highway, a transition zone where particles from inside the heliosphere and particles from interstellar space appeared to be moving freely in both directions, leaking back and forth along connected magnetic field lines that stretched across the boundary rather than stopping cleanly at it. That detail matters enormously because it directly contradicts the simple image most people, including most scientists at the time, had in their heads of what crossing into interstellar space should actually look like. The expectation was something closer to a wall, a clear, describable threshold where you're unambiguously inside the solar system one moment and unambiguously outside it the next. What Voyager 1 found instead was something closer to a porous membrane, a region where the two environments were actively blending and exchanging material along magnetic field lines that connected across the supposed boundary rather than a hard, describable edge separating them. Then, on August 25, 2012, Voyager 1 finally crossed what scientists now recognize as the true heliopause. And this time, the data was genuinely dramatic. The number of charged solar particles surrounding the spacecraft dropped by roughly 1,000-fold in a remarkably short span, while the number of high-energy cosmic rays originating from outside the solar system spiked upward by about 9%. Both of those readings happened abruptly, exactly the kind of clean, describable signature scientists had originally expected to see at the true edge of the solar system. So, in that narrow sense, Voyager 1 finally did find something resembling the wall physicists had predicted, a genuinely sharp, sudden transition in particle populations. But the magnetic field data once again refused to cooperate with that clean picture. Instead of swinging to a dramatically different orientation the way theory predicted for a spacecraft entering an entirely different magnetic environment, the field barely changed direction at all. It grew noticeably stronger, consistent, with compression right at the boundary, but it kept pointing in almost the same direction it had before the crossing. So Voyager 1 delivered scientists two seemingly contradictory stories happening at the exact same location, an abrupt, wall-like transition in particle density, layered directly on top of a smooth, almost undetectable transition in magnetic field direction, the exact opposite of what a simple, unified model of the boundary would have predicted for both measurements simultaneously. It took years of additional research to reconcile these seemingly conflicting signals into something resembling a coherent explanation. A team led by astrophysicist Nathan Schwadron at the University of New Hampshire eventually combined Voyager 1's readings with data from 3 independent missions, including NASA's Interstellar Boundary Explorer, which had previously discovered a strange, ribbon-shaped feature believed to trace the true direction of the undisturbed interstellar magnetic field. By cross-referencing all of these datasets, collected over roughly 25 years, using entirely different instruments and techniques, the team found that the true interstellar magnetic field wasn't actually absent from Voyager 1's readings. It was simply draped and bent around the heliosphere's shape, the way a stretched rubber band bends around the curved surface of a beach ball, rather than slicing straight across it. Voyager 1's magnetic field really had been slowly rotating toward that true interstellar orientation the entire time, just far more gradually than a simple, sharp boundary model ever anticipated. Later research pushed this picture even further. Scientists studying the region now believe that magnetic field lines from inside and outside the heliosphere don't just meet at the boundary, they actively pile up, twist, and in some cases break apart and reconnect entirely, a process called magnetic reconnection, releasing bursts of energy in the process. Some researchers have proposed that narrow tunnels of connected magnetic field, called flux tubes, may allow small amounts of solar material to genuinely leak directly out into interstellar space through the boundary, and vice versa, which would help explain exactly the kind of two-way particle traffic Voyager 1 detected during its months spent drifting through the magnetic highway before the final crossing. Put all of this together, and the picture that emerges is genuinely strange when compared to what most people, understandably, still picture when they imagine the edge of the solar system. It's not a hard, describable wall. It's also not a slow, gentle, uniform fade, the way early models suggested either. It's something structurally messier and more interesting than either simple picture, a boundary that's simultaneously abrupt in some measurements and gradual in others, thinner in some directions than models predicted and threaded through with magnetic tunnels that allow particles to move across it in ways nobody originally anticipated. Astrophysicist Merav Ofer, who has studied this region extensively, later reflected that scientists probably shouldn't have been quite so surprised by that complexity in hindsight, given how genuinely dynamic and layered the interface between two entirely different magnetic environments was always likely to be. Voyager 2 later added its own confirmation to parts of this picture when it crossed into interstellar space in November 2018, 6 years after its twin, at a completely different location along the boundary. Interestingly, Voyager 2 crossed the termination shock and heliopause much closer together in distance than Voyager 1 had, providing direct proof that the heliosphere isn't a simple sphere at all, but a lopsided asymmetric shape, closer to a teardrop, thicker in some directions and noticeably thinner in others depending on how the interstellar medium happens to be pressing against it from outside. There's also the matter of temperature at this same boundary, which adds yet another layer of strangeness to the story. Both spacecraft recorded regions right around the heliopause, where temperatures spiked to between 30,000 and 50,000 Kelvin, hotter than the surface of most stars, a discovery researchers have informally nicknamed the Wall of Fire. That extreme heat comes from individual charged particles moving at extraordinary speeds, even though the region is so sparse that there's nowhere near enough material present to transfer that energy the way heat would here on Earth, which is exactly why both spacecraft passed straight through it without any damage at all. Even that temperature spike ties back to the same underlying theme running through this entire boundary, energy being released and particles being accelerated through exactly the kind of magnetic compression and reconnection processes that made the whole region so much messier and more dynamic than the simple, layered model scientists started out with. What makes this entire story such a genuinely compelling example of how science actually works is that none of these apparent contradictions turned out to mean Voyager's instruments were malfunctioning or that the data was somehow unreliable. Reality at the edge of the solar system simply turned out to be more structurally rich and more physically active than the simplified model scientists had built to predict it. And it took years of painstaking cross-referencing between multiple independent missions to fully piece that reality together from what Voyager 1 alone had recorded. Both Voyager spacecraft continue transmitting today, still gathering data from the far side of that same boundary, even as their nuclear power sources steadily decay and engineers back on. Earth make increasingly difficult decisions about which instruments to keep running. NASA officials estimate both missions could realistically continue for another few years before power finally drops too low to keep anything functioning at all. Every additional data point either spacecraft manages to send back adds another piece to an already far stranger picture of the true edge of our solar system than anyone predicted before these two aging machines actually made it there. If a story like this, a supposed wall at the edge of the solar system that turned out to be thinner, more porous, and far stranger than physics predicted, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment letting me know which part of this boundary surprised you the most, and stick around because there's a real chance these two remarkable spacecraft still have more waiting in the data they haven't fully explained yet.